Okay, this is a description of the solutions to problem set 4. Okay, you are um, familiar with the problem, so I won't go through reading the problem. For the first problem, we have a sled and a block, the free body diagram, first of all, of the block. Here's the free body diagram of the block. We have forces acting on the block, the tension of the string pulling to the left. We know the block will accelerate to the right along with the sled, and therefore there must be a force, and that is the friction force, the force exerted by the sled on the block to the right. Of course, there's the weight and the normal force up and down. Now for the forces acting on the sled. There are actually two strings attached to the sled, the top string and the bottom string, each with the same tension, F. Tensions are the same because they're the same string. Of course, there are up and down forces, and those are going to cancel. But because there is a force exerted by the friction force exerted by the sled on the block, there must be a force exerted by the block on the sled equal and opposite. These are action-reaction pairs. And so that's the free body diagram of the sled. Now if I add these two together, I will end up with the free body diagram of the system. And in doing so, you notice that the friction forces cancel. Those are internal forces. One of the tension on the sled cancels with the tension on the block. And so besides the vertical forces, the only force acting on the system is F. Okay, so, oops. Find the common acceleration of the static friction force. If I look at the system, F net equals ma, the net force on the system, looking at the system free body diagram, is F equals the mass of the system, which is m and m. Solving for acceleration, we get this value here. Now to find the friction force, I have to look at either the block or the sled. I think in this case I look at the block, and here's the free body diagram of the block. The net force on the block equals the mass on the block times its acceleration. The net force on the block is Fs minus F. Again, substituting in from the value of A and doing some algebra, we end up with an expression for the friction force. In problem 2, we have a car on a bank, 24-degree bank track, traveling in a circular path. The free body diagram, since there is no friction, the forces are weight downward, the normal force upward. To determine the speed for which this curve is appropriate. The important point here is that since the radiator inward direction is on the x-axis, we have to set up our axes x horizontal and y vertical. In the vertical direction, the y direction, net force must be 0, so mg must be equal to n cosine 24 degrees. In the x direction, the net force must be mv squared over r, and that is just the component of n, the x component of n. So n sine theta must be mv squared over r. Substituting in for n, we find from the y equation, we end up with v equals the root of gr tan theta. Substituting values gives us 31.7 meters per second. If there is we're going to negotiate the curve at much higher speed, 100 meters per second, and so that's going to require more inward force, and that's going to be provided by a friction force. So the friction force directed down the ramp. Again, we construct our axes in the same direction, with x horizontal and y vertical. In the y direction, that force must be equal to 0. We have mg and fs sine theta going downward must be equal to n cosine theta going upward. Doing the algebra, I can get an expression for n. In the x direction, there is n sine theta, as well as the fs times cosine theta must be equal to mv squared over r. And that gives me an equation in terms of n and mu. If I substitute in the previous value for mu into the equation, and I do some algebra, actually a lot of algebra, I end up with an expression for mu. I end up with mu of 1.34, which is very unusual or impossible, because mu value should be less than 1. So this mu value is really not possible. Calculating the number of g's, we're going to calculate the acceleration the driver feels, which is v squared over r, and divide that by 9.8 meters per second squared to give me 4.4 g's. For problem 3, we have a free body diagram of M1, free body diagram of M2, and equations. Net force on M1T minus M1G equals M1A, and for M2T minus M2G equals M2A. In writing these equations, I've used the convention that everything upward, accelerations upward, tensions upward are positive, and downward are negative. And I adopt this because I don't really know whether the acceleration will be positive or negative, whether upward or downward. Now, in the frame of reference of the pulley, I know that M1 and M2 will have equal but opposite accelerations, and I'm going to call that acceleration in the frame of reference of the pulley a rel. What this means is A1 will be A minus A rel, and A2 will be A plus A rel. And so really what I have are 4 different equations. 3, 4, and I'm going to solve. A lot of algebra later, I end up with solutions for A1, for A2, and for tension. If I want to check this out, I know that for the situation where M1 and equals M2, everything should be accelerating upward with the same acceleration A. For M1 equals M2, the second term here becomes 0. The first term just becomes equal to A, so A2 equals A. In the expression for A1, again, the second term becomes 0. And the first term, once again, if M1 equals M2, is equal to A. And so, in this situation, we see that for M1 equals M2, A1 and A2 both equal A. So that gives us at least plausible results. And I can note that all my solutions are dimensionally correct, so pretty good chance that these are in fact correct answers. Okay, that's it.